This was the first slide, and it showed the picture of a brownie cake and this norm which I'm defining on the next slide. Okay, so you haven't missed anything, those of you who are online. Okay, so what is the p-adic norm? P is a prime number. Choose your favorite prime, 2, 3, 5, 7. I think everyone knows what a prime number is. And x is a non-zero rational number. So as I said, something like 2/3, 5/6. Take two integers and divide them. Right? That's a rational number. Yeah. So things that are not rational, I think you have seen things like that. For example, √2 is not a rational number. I think that was a proof which was given sometime in the course. I don't remember in which, not my course, but some course. Right. So you know, not all numbers, in fact most numbers are not rational. So you choose a rational number and you have a prime number, and then if you have this rational number, then you write it as p to the n times a divided by b, where a and b are integers and they are co-prime to b, meaning they don't have factors of p, right. So all the powers of p that you have in the numerator and denominator of this rational number, you take those out, then you cancel whatever can get cancelled and whatever is remaining. So this n could be negative also, right. So it could have a form like, for example, if p is 2 and this is, let's say, 8 by 12, then you first take all the 2's out, so that is 2 to the power 3 divided by 4 times, so 2 squared times 3, and then you cancel the powers of 2, so you have a 2 left on the top, and then you have something else which is of the form a by b, where those are, so 1 by 3, where they are co-prime to b. Okay, so any number can be, any rational number can be expressed in this form, and then you define this norm to be p to the power minus n. Okay, this is a very weird norm, right. Usually when you think of norms, at least when we have done calculus, you have thought in terms of distances, right. So you should also think of this as a distance, but it's not a distance that you physically imagine. And let's there's one number remaining for which I should tell you what the norm is. So x is a non-zero rational number. You define norm of 0 to be 0. Okay, so let's just to set ideas, let's just do a couple of examples. So for example, if I have 1 by 5 and I do the norm of 5, what would this be? So this is 5 to the power minus 1 times 1 by 1, so that's your n. So the norm, sorry, this is not 5 to the power minus 1 times 1, 1 by 5 can be written in this way. So 1 by 5 can be written as 5 to the minus 1 times 1 by 1, and that's your n. So you do 1, so 5 to the power 1, so this is 5. Okay, that's the norm. Okay, if you have 2/3 with respect to 2, then so 2/3 is, you pull 2 out, you multiply this by 1/3, and this is now a and b are co-prime, so you have 2 to the power 1, so the norm is 1 by 2. Okay, it's a weird norm, you need to get used to this norm. Yeah, if you don't, I mean, the first time you see it, it's not something that will that you can imagine quickly, right. When you have distance, it's something that's physically, you have an intuition about it. Okay, so this is not something that you can quickly imagine. So yeah, so 2 or 3 things that first let's sort of mention for what's coming ahead. What is the norm of 1 with respect to any p? So the norm of 1 with respect to any p is 1, because you can write 1 as p to the power 0 times 1 by 1. So you have 1 by p to the power minus 0, which is p to the power 0, which is 1, right. So the norm of 1 is 1, and maybe 2 or 3 other norms that I will be useful as we go ahead. So what is the norm of half with respect to 2? This is similar to 1 by 5 with respect to 5, that's 2. So this is something you should remember for what's coming. And if you take an integer, So if you take an integer, right, n is an integer, and its norm is, so I really, in this talk I really want to focus on 2. So let's do this with 2, right. Suppose I know that this norm is less than 1, okay, this is less than 1. This is exactly the same statement as saying that 2 divides n, right, because the norms can only take values like 2 to the power something, if you remember what the norm was, right. So if it's less than 1, that means it's 1 by 2 to the power something, that means n itself will be 2 to the power something. So it's, in particular, it's divisible by 2, okay. This is what is important for what's coming, okay. These two things, if nothing else, these are the two things you should remember, okay. So I hope these examples give you some feeling for the norm. This is a weird thing, right, because as you can see, if you take norm of 1 by 5, that's 5, but if you take norm of, with respect to 5, but if you take norm of 5, that's 1 by 5, right. So in some sense 5 has a smaller norm than 1 by 5. Yeah, this is completely unintuitive. When you do usual calculus or geometry, if something is far away from 0, then it usually has a large norm. If something is close to 0, it has a small norm, right. That's what distance is about. But here exactly the opposite is happening. Yeah, norm of 5 is 1 by 5, but the norm of 1 by 5 is 5. In fact, norm of 1 by 5 squared will be 5 squared, so it's even larger. Yeah, so this is a very weird norm. Okay, so why care, right? Maybe first we can ask why care. So the reason we care, one of the reasons, is that this norm somehow picks up division. So this last part, right? So if you want to understand when a number is divisible by some prime, you can calculate its norm with respect to that prime, and from there you can conclude about whether this prime divides that number. Okay, that's the main motivation for defining this norm. Okay, now of course I'm saying this is a norm. I mean, I just claimed that. Why is it a norm? So maybe let's see why that is the case. Okay, so first I talked about distance. So just to recall, for not everyone may have done maths too. So once you have a norm, you can always define a distance. So the distance is, if you have two numbers, so in these case they are rational numbers x and y, the distance between x and y is, you take that difference, that's still a rational number, and you take the norm of that with respect to p. Okay, that's this is a standard definition for any norm. This is also how we did distance when we did maths 2, for those of you who have done maths 2. Okay, so the norm comes with some property, right? I have to check some properties in order to say something is a norm. One of those properties is that it's multiplicative. So let's quickly check that's the case. So suppose you have two numbers x and y, and I take the norm with respect to p, then I claim that that's the same as taking norm with respect to x, norm of x multiplied by norm of y. Okay, so x, let's write x as p to the n a by b, y as p to the n prime a prime by b prime. Now a, b, a prime, b prime are not divisible by p, that means they are co-prime to p. So when I multiply, x, y is p to the n plus n prime a prime by b prime, right? And this is exactly the form that we require in order to say what the norm is. So this will tell us that the norm of xy is 1 over p to the n plus n prime, which is exactly 1 over p to the n times 1 over p to the n prime. The first thing is norm of x, the second thing is norm of y. So this is multiplicative. This is an easy statement here. Yeah. Now I used p is a prime here, although I didn't. I wrote this all down very quickly. And where did I use it? I used it to say that a times a prime is also co-prime to p, and b times b prime is also co-prime to b. Yeah, if p is not prime, this may not happen. Yeah, so because a is not divisible by p, a prime is not divisible by p, so a times a prime also is not divisible by p. If p were not prime, we could not have made that statement. Okay, so I am using p is prime here. Okay, the other property that we need to say something is a norm is what is usually called the triangle inequality, and what drives this particular norm is a much stronger version of the triangle inequality. So it's called the ultrametric property. This is something massively powerful, much more stronger than the triangle inequality. Okay, so here's what it says. It says norm of x plus y with respect to p, it's not just less than or equal to norm of x plus norm of y, it's actually less than or equal to the maximum of the norms of x and norm of y. Okay, so this is much more powerful. Yeah, it's giving a much stronger inequality than the one we need, the triangle inequality. Right, and yeah, I had a proof of this, but it's 9:20, maybe not a good idea to go through this proof. So if there's time, I'll come back and prove this. Okay, so this norm satisfies a very strong version of the triangle inequality, which is that norm of x plus y is less than or equal to the maximum of the two norms that of the numbers that you're adding. Okay. Now, if I had gone through the proof, I would actually have proved something more, which is what we are going to use. So, which is the following statement, that if it so happens that norm of x is not equal to norm of y, right? It could happen that norm of x is equal to norm of y, right? Then the norm of x plus y is actually equal to the maximum, not just less than or equal to, it's actually equal to the maximum. So maybe instead of giving a proof, what I'll do is I'll give an example of this. Let's do an example of computing these inequalities, right? So suppose I take my x is half and y is maybe 2/3, and I take p to be 2. Let's see what is norm of x. So norm of x is 2, norm of y is 1/2, and let's compute what is x plus y. So x plus y is half plus 2/3, so that's 3 plus 4 divided by 6, so 7 by 6. Correct me if I am wrong, I am doing this real time, so I have not prepared this. Yeah. So, right, I should put the 2 there. Right. So this is norm of 7 by 6 with respect to 2, and so now you express 7 by 6 as you pull out all the factors of 2. So you have half times 7 by 3. So the norm here is 2. So as you can see, this is equal to the maximum of the norms. Yeah. The norm of x plus y with respect to 2 is 2, which is the maximum of norm of x and norm of y. Okay. Now I am not claiming this is a proof, I am just saying this is an example. Okay. If there's time, maybe I'll come back and give you a proof. In general, it may not happen that it's equal if x is equal. For example, you could have a situation where x is equal to minus y, right? Y is equal to minus x. Then if you take x plus y, that is 0. So the norm of 0 is 0, as we know, and that's going to be, if x and y are non-zero, then that maximum will be strictly greater than 0. So in general, the inequality is the best you can say, but if the norms of x and norm of y are different, then the norm of x plus y is equal to the maximum of these norms. This is very different from the geometry that we see in the Euclidean plane, right? So there's a colloquial statement when you do this kind of so-called p-adic analysis. They say that every triangle is isosceles in this world, and it's referring to this identity, because if you think of this, the triangle inequality is sort of where you draw this triangle, right, and you think of x and y and something like x plus y over here, and what this is saying is either these two sides are equal, and if they are not, then this x plus y type side is equal to this one or that one. Yeah, I mean, this is a colloquial statement, you don't interpret this explicitly, because this is not geometry, as you can see, right? But so in this world, sort of isosceles triangles are always isosceles. Yeah, this is a colloquial statement for remembering this. Okay, so this is a very important identity. We'll use this as we go ahead. Fine. So this is all about the p-adic norm. Okay, so I may have put some of you off because what is this? He's going back to high school. God, I forgot how to divide numbers, etc. Fine. Don't divide numbers. Now let's divide cakes. Okay. So let's start doing this. So So here's a brownie cake, and so one of my friends, he decided, okay, I won't make a, you know, usually you have cakes which are round and you cut them, etc. So he decided I'll make a brownie cake. Typically they are squares or rectangles, and it was his son's birthday, and then he made the cake. He was very happy. Son came back with some friends, and the son looked at it and said, hey, he said, okay, now let me cut it. Usually when you do brownies, you cut them into sort of square or rectangular pieces, right? Son was very disappointed. He said, no, I don't like this. Usually we have a round cake and then you slice it into like this. And I want that thing. My friend was very disappointed. He said, but I made a square cake or a rectangular cake. So the son said, okay, fine. So that's fine. So maybe instead of square pieces, you make triangular pieces. So at least it's coming close to the usual round cake. Okay, so slice it in the usual way into triangles. And of course, these are all small kids. Each one wants as much as the other. So he came with 6 friends, and with him there were 7 total. So there was a square cake with 7 children, and then my friend started thinking, how do I cut this into 7 pieces? Seems like a difficult problem. So let's see, how do you cut a square into triangular pieces, all of which have the same area, okay, because you don't want any kid to have less, right? Otherwise they are going to throw a tantrum, right? So here's some ways of cutting into equal triangles, okay, they all have equal areas, okay. You can slice it down a diagonal, there are 2. You can do the same thing with the other diagonal, there are 4. You can cut, you know, the sides, there's 8. Okay, whoops, what happened? Can yeah, I don't know, someone else started sharing this. I mean, yeah, so I'm fairly sure others have many interesting things to say which are probably more interesting than this, but for the next 20 minutes at least, bear with me. Okay, so you cut it into these squares into these possible ways. I've given you some ways that you could naturally think of cutting it into triangles of equal area, right? In each of these cuttings, each triangle has the same area, okay. And how many are there? Well, there's 2 here, there's 4 slices here, there's 8 slices here, there's again 8 slices here. How many are there here? 1, 2, 3, 4, 5, 6, 7, 8. Again 8 slices here. Seems to be like they are always multiples of 2, right? So my friend called me and said, hey, I want to cut it into equal areas, slice it, and but I need 7 slices. How do I do that? And it turns out that this is a problem which this is a question that other people have asked before. So can a square be sliced into an odd number of triangles of equal area? Yeah, this is the question, right? This is, now you can convert this to a math question like this, okay. So this is a historical note. This question was asked by someone named Fred Richman, and it was popularized along with another mathematician named John Thomas, the 60s. And it turned, I mean, this seems like a very simple question to ask, right? Turns out no one knew the answer to this. I mean, this is a usual, you would think, oh, this is known from some Euclid, and you know, we study all kinds of things in geometry, Euclidean geometry, and something you would know from there. Turns out no one knew the answer, so they asked the question in the monthly in 65, and the proof was given by someone named Monsky. He is a very famous mathematician, and Monsky's theorem says that suppose a square is sliced into triangles of equal area, then the number of triangles must be even. There is no way of doing it so that it's odd, okay. So unfortunately my friend had to be disappointed, so I just told him, well, what you do is you cut it into 8 parts and you eat one yourself. So take one for yourself. Okay, so and yeah, so this is the theorem, and in the remaining 15 minutes, I'll see how much time I have, how much I can do. I'll try to answer this question, and surprisingly, there's only one known proof, only one, and that known proof goes through the p-adic norm. Okay, only one. You would expect this is a very, this is something you could do using Euclidean geometry. Seems like a very easy question. I mean, I could maybe twist things around, use some kind of tests that I've learnt in high school. No, it doesn't work. In fact, there's only one theorem, and it's a very beautiful and elegant proof. Yeah. So you don't need to know any, at this point you don't need to know any mathematics other than the two things that I mentioned, that the p-adic norm of half, what is that, the p-adic norm of an integer, what is that, and that ultrametric property. These are the only three things that you need. Okay, all three I have stated. Yeah, so you have to remember that. Okay, and now we'll come to answering this, how to prove this theorem. Okay, so the first thing you need in answering this theorem is something called Sperner's lemma. This is a very interesting lemma in itself, and so I'll state it, and then I'll try to sketch a proof. So Sperner's lemma says the following. So suppose you have a polygon which is divided into triangles. Yeah, so we were in particular thinking of a square, right? You take any polygon and you divide it into triangles. Okay, so you color each vertex with one of the colors red, blue or green. Okay, you can do it in any way you want. You take those vertices. So you have these triangles. Each triangle, it has 3 vertices. So you have a bunch of vertices. You color them with red, blue or green. Okay, three colors. Let T be the number of triangles with each vertex having a different color. Okay, so triangles which have one red vertex, one green vertex and one blue vertex. Okay, so I'll call such triangles RBG triangles. Okay, they have one red, one blue and one green triangle vertex. Okay, so you count the number of such triangles, call that T. Okay, you count one more thing, the number of edges on the boundary whose endpoints are colored red and blue. Okay, so call that number T, S, and it turns out, this is Sperner's lemma, that the difference of S and T is always an even number. Okay, so something to do with what we want. Okay, so let me sketch this out in GeoGebra. Let's see if I can do this. So here's a polygon, and except that I have forgotten how to use this. I can use my mouse. So I have to share this again. Oh my god. Okay. Okay, sorry. Those of you online, I'll just apologies. As I said, I'm really technologically challenged. Yeah. So let's do this example in GeoGebra. So here's a polygon, and let's triangulate it. So let's see if I can draw all these triangles. No, so this is not what I want. I want to draw the line so that I get triangles. So okay, so here's a triangulation, and I've also colored them red, blue and green, right? Each vertex I've colored red, blue or green. Okay, and the triangles which are RBG triangles I have in a different color. So here's one RBG triangle, here's one, then here's another, right? So I have 1, 2, 3, 4, 5, 6, 7 triangles which are red, blue, green triangles. Okay, and now let's count the number of edges on the boundary which are red, blue. Okay, so I have this top edge F which is red, blue, so 1. Then I have this edge NO which is red, so 2. Then I don't know why this point has come out. Anyway, Okay, anyway, there's a point which is outside which should not have been there. I think something got changed when I opened it. Anyway, so then there's another red blue which is the side A, which is AB. Okay, so totally how many red blue sides are there? There are 3. Okay, and how many triangles are there? 7. And what's the difference? 4, which is divisible by 2. Okay, so again, this is the illustration of Sperner's lemma, and actually the proof is extremely easy. So I think I'll just very quickly, since every math talk should have at least one proof. So let's do this proof. So here's your polygon, and suppose you triangulate it in some way. Okay, fine. So now we have, we can color these. Suppose I color these in some way. So here's some reds, here's some blues. Okay, I haven't probably done a good job. Oh, sorry, there's nothing here. Yeah, sorry, this should not have been. Right. So what you do is, every time you see a red blue edge in this picture, you put 2 dots on either side of it. Okay, you put a dot here. Oh, sorry, this is not red blue. Yeah, this is red blue. You put a dot on either side. Okay, this is red blue. You put a dot on either side. Dot on either side. Dot either side. Dot on either side. Dot on either side. Dot on either. I think I've done all of them, right? So I put a dot on either side of the red blue edges. Okay, now let's count the number of dots in the polygon. Okay, how many are there? Okay, so every red blue side which is inside the polygon, yeah, like this one here, right, this one here, right, that gives you 2 dots which are inside the polygon. Okay, so this is 2 times number of edges, meaning red blue edges in the polygon. Okay, and then every red blue side which is on the boundary, that gives you only 1 dot, because the other dot is outside the polygon, right. So this is 1 times the number of red blue edges on the boundary. Yeah, is this okay? I think this is, oops. Yeah. So I hope this is clear. On the other hand, I can also count the same number by looking at triangles. So based on each triangle, I'll try to count the number of dots. Okay, so if you go up, you take a red, blue, green triangle. In this picture there's 1, and you can see there's 1 dot inside that triangle. Okay, on the other hand, if you have triangles which have either 2 reds or 2 blues, they contribute 2 dots. For example, this triangle here, it has 2 dots, right. So yeah, yeah, this is my pointer. I was wondering why there was a dot over there. Okay, yeah, so they have 2 if you have a red, blue, green triangle, they have 1 dot. And every other triangle which is of the type red, red, blue, or red, blue, blue, will give you 2 dots, right, and any other triangle will not give you any dot. So these are the only ways in which you can have dots. Okay, okay. So now what did we want to compare? We want to compare this term over here, the number of red, blue edges on the boundary, with this term over here, the number of red, blue, green triangles. and what do you see? The difference is 2 times something, right? Because these two numbers are, I mean, the number of dots in the polygon we have counted in 2 ways. So if you take the difference, it's 2 times something. Yeah, so this is the proof of Sperner's lemma. Good. So we have done one proof. Now I may not be able to complete anything else, but I have done at least one proof. Okay. So now we have to apply Sperner's lemma to our problem, right? What was our problem? You take a square and you slice it into equal triangles of equal area, and you want to show that the number of triangles is an even number, right? That's the aim. Okay, so I have only 4 more minutes, so I can't complete the proof clearly, but I'll sketch it. Okay, so the proof is through this really clever trick, and this is like the heart of the proof. Okay, it's just a simple one line statement, and then you can do the rest yourself. So you first of all you can think of your square as sitting at 0 0 1 0 0 1 and 1 1. Okay, and so now you divide it, and for the time being assume that all these vertices, their coordinates are rational numbers. Okay, this may not happen, I am not claiming this always happens, but assume this for the time being. Okay, so if you draw your slices, every vertex that you get, those coordinates are rational numbers like half, comma, 3/4 or something like that. Okay. Okay, so now you color these vertices according to the following scheme. So you color it red if the x coordinate norm with respect to 2, so now your p-adic norm has come in, is less than 1, and the y coordinate norm is less than 1. You color it blue if the norm of x is bigger than or equal to 1 and the norm of x is also bigger than or equal to norm of y, and you color it green if the norm of y is bigger than or equal to 1 and the norm of y is strictly bigger than norm of x, and this exhausts all possible choices for what can happen to a vertex. Okay, so every vertex will get some color in this way. Okay, and so let's see our square here. So here's the square. First let's ask what happens to the vertices of the original square itself. Okay, so there's 0 0, right? So the norm of 0 is 0, so each coordinate has norm 0, so according to the previous scheme it will have color red because norm of x is less than 1, norm of y is less than 1, so it will have color red, so it is red colored. Okay, similarly if you take the point 1 0, then let's go back. So the norm of 1 was 1, so the norm of x is bigger than or equal to 1 and the norm of 0 is 0, so norm of 1 is bigger than or equal to norm of 0, so it will have the color blue. Okay, so here it has color blue. Okay, if you take the point 1 comma 1, then norm of 1 is 1, norm of 1 is 1, so again it will have the color blue, and finally if you take 0 comma 1, you can check that it will have it will have color green. Okay, okay, so now here's the important point. On this edge C, so the edge connecting the vertices C and D, yeah, the x coordinate for any, suppose a vertex lands on that line, on that segment, then the x coordinate must be what is the x coordinate there? 1, right? So the norm of that is 1. So you can check that no red vertex can come there because the red vertex was that norm of x is strictly less than 1. So it can't come on this segment here, right? Similarly, since norm of y is 1 on this top one, you can't have any red vertex on this one. Okay, and similarly you can have no blue vertex here. So the point is we want to apply Sperner's lemma, right? And in Sperner's lemma you calculate the number of red blue edges on the boundary. But what are we seeing? There can be no red blue edges on these three boundaries. So the red blue edge, if at all there is any red blue edge, it must come on the bottom boundary, because it must be on the bottom boundary. And how many can there be? There can be only an odd number. Why is that? Because suppose you have some vertices here, right? So you have a red one here, then you maybe have a blue one. I can't change. Suppose you have like a series of red, blue, yeah. But the starting point is red and the ending point is blue. So if you calculate how many segments will be red blue, it must be an odd number. Yeah, you can check this. Yeah, think about how many times do you flip, right, from red to blue, because eventually it must be blue. Yeah, you're starting with red and ending with blue, so it must be odd. Yeah, so the number of boundary segments which are red blue must be odd. But now we can apply Sperner's lemma. So Sperner's lemma now tells us that when you cut this triangle and apply those red blue things to your vertices, there must be an odd number of red blue green triangles. Yeah, that was Sperner's lemma, right? That the difference is even. So that means there is an odd number of red blue green triangles. In particular, there must be at least one red blue green triangle. Yeah, that is the main sort of punchline. Now once you have a red blue green triangle, we can compute its area. So I don't have time now, Arun is here already. So I won't do this proof, you can do this. What you do is, you have, you take the endpoints, so you call them xr, yr, xg, yg, xb, yb for each of those vertices. You have to first check that, suppose you shift xr, yr to the origin, right? So then you get your points, the triangle is shifted to the origin, right? The vertices don't change color. Okay, for this you have to use the ultrametric statement. Okay, and then again, so then eventually what you will have is, you will have xb, yb, which is the blue one, xg, yg, which is the green one, and 0, 0. This is how your triangle is going to look like. Yeah, it may be something like this. Okay, so this is maybe xb, yb, this is xg, yg. Okay, but now we know how to compute the area of a triangle, right? This is something we have done in high school. So this is half times xg, yg, xb, yb, right? So this is half times xg, yb minus yg, xb. This is the area, right? Now let's compute the p-adic, the 2-adic norm of this area. Okay, so this is norm of half times the norm of this xg, yb minus yg, xb. But there's something we know here. This guy, let's look at when something was colored green and something was colored blue. So we know when that happens. So this xg, yb and xb, yg, so this here xb always has norm bigger than or equal to yb, and xg or yg always has norm strictly bigger than xg. So this has norm strictly bigger than this. So by that ultrametric thing, this entire norm is actually the norm of yg, xb. But both these norms are bigger than 1. That was how we arranged it. So this entire norm is just greater than or equal to whatever was the norm of half. And what was the norm of half? It was 2. And now this is the punchline, this ends the proof, because now suppose the number of triangles is n. Remember that all the triangles have the same area, right? So n times area is the area of the square, which is 1. Apply your norm. So what is norm of 1? This is 1. What is the this norm of the area, it was, let's go back, it was bigger than or equal to 2. So that means the number of triangles, this is less than or equal to half. Aha, but n is an integer, and anytime it's strictly less than 1, what does this say? This means that n is divisible by 2. Yeah, this completes the proof. Okay, so this is a very beautiful proof, and yeah, I thought this was something that might be interesting. One last comment, I made an assumption. I said all the vertices must be rational. Maybe they are not, right? So there you need to do a little bit more of, not hard, but you need to know the fact that this norm you can extend not just to rationals, you can actually extend it to the real line. That needs some, it's not an explicit proof, it's an existential proof. So I can't write down if I take a number what the norm is, but it exists. Yeah, so and then the same analysis works. Okay, so that's the proof. Okay, so the moral of the story is that my friend had a brownie himself. Thank you. Yeah, any questions I can. Yeah, sorry I'm over time, but I think I started a couple of minutes late.
Any questions?
Yeah. Okay.
I can speak like this. Sperner's lemma seemed very interesting.
Okay.
So, is it so that when we are coloring the vertices, like it's like the first time I'm seeing Sperner's lemma.
Sure.
So, it seems like that at least we will have one triangle where all the three vertices will be of different color. Is it so?
No. No, you can just color every vertex red, right, for example. Then, yeah, so that need not happen. But Sperner's lemma still holds, if you think of, because there's zero number of edges on the boundary and there's zero number of RBG triangles. So, yeah, there's no, I mean, yeah, but that need not happen. It need not happen that it always exists.